SP2 hybridization explained. In this lecture, I will explain SP2 hybridization in complete detail with examples. After watching this video, you will fully understand how SP2 hybridization works in different molecules. So let us begin. First, we need to understand how we can define SP2 hybridization. The type of hybridization in which one s and two p atomic orbitals mix together and form three sp2 hybridized orbitals is called SP2 hybridization. Now, before we move further, there is one important rule about hybridization that you must always keep in mind. The rule is that the number of atomic orbitals that mix together will always be equal to the number of hybrid orbitals that are formed. For example, here in sp2 hybridization, one s orbital and two p orbitals are mixing together. That means three atomic orbitals are mixing. So, according to this rule, three hybrid orbitals will always be formed. And you need to keep in mind that this rule applies to every type of hybridization. Now I will tell you about the shapes of these orbitals. As we know, the shape of s orbital is spherical, and the shape of p orbital is dumbbell. When we look at this through a diagram, one s orbital which has spherical shape mixes with two p orbitals which are px orbital and py orbital. These three orbitals mix together and form three sp2 hybridized orbitals. If we look at the overall shape of these sp2 hybrid orbitals, their arrangement is trigonal planar. To understand sp2 hybridization in complete detail, we will cover three examples. In the first example, we will understand sp2 hybridization in BF3. In the second example, we will see sp2 hybridization in ethene molecule. And in the third example, we will cover sp2 hybridization in benzene. Let's start with the first example. If we look at the BF3 molecule, as it is clear from the formula, the central atom here is boron, and three fluorine atoms have formed bonds with boron. Now, before explaining the electronic configuration, I will share a very useful trick with you. Using this trick, you can find the hybridization of any specific atom in any molecule very quickly. The trick is this. First, write the expanded structure of the molecule. Expanded structure means open all the bonds and write them separately. Then count all those bonds. The number you get will be the steric number of that atom. And the hybridization type in which the number of hybrid orbitals equals that steric number will be the hybridization of that atom. Let's apply this trick on boron in BF3. When we write the expanded structure of BF3, it becomes clear that boron is forming three bonds, one bond with each fluorine atom. So the steric number of boron is 3. Now sp2 hybridization gives us three hybrid orbitals. Therefore, the hybridization of boron in BF3 is sp2. Now look at the electronic configuration of boron. The atomic number of boron is 5. This means boron has 5 electrons. The ground state electronic configuration of boron is 1s2, 2s2, 2px1, 2py0, 2pz0. In this ground state, boron has only one unpaired electron, but boron needs to form 3 bonds with 3 fluorine atoms. So boron needs 3 unpaired electrons. To get 3 unpaired electrons, one electron from the 2s orbital gets excited. This electron moves from 2s orbital and goes into the empty 2py orbital. Now the excited state electronic configuration of boron becomes 1s2, 2s1, 2px1, 2py1, 2pz0. Here, always remember one important point. The electron will always be excited from the 2s orbital only. The electron from 1s orbital will never get excited. The reason is that 1s is not the valence shell of boron. Only valence shell electrons participate in hybridization and bonding. Now hybridization takes place. The s orbital and the 2p orbitals, which are 2px and 2py, mix together. According to the rule of hybridization, 3 sp2 hybrid orbitals are formed. These 3 sp2 orbitals form 3 bonds with 3 fluorine atoms. The shape of BF3 molecule is trigonal planar, and the bond angle in BF3 is 120 degrees. Now let's move to the second example. That is the ethene molecule. In ethene, the central atom is carbon. Let us apply the same trick here. First, write the expanded structure of ethene. When we open the structure of ethene, it becomes clear that each carbon is forming a double bond with the other carbon. And along with that, each carbon also has 2 hydrogen atoms attached to it. Now, if we count the characters of carbon, we have 2 single bonds with 2 hydrogen atoms and 1 double bond with the other carbon. These make a total of 3 characters for carbon. So the steric number of carbon is 3. And since SP2 hybridization gives 3 hybrid orbitals, the hybridization of carbon in ethene is SP2. Now let's look at the electronic configuration of carbon. The atomic number of carbon is 6. The ground state electronic configuration of carbon is 1s2, 2s2, 2px1, 2py1, 2pz0. In this ground state, carbon already has 2 unpaired electrons in 2px and 2py orbitals. But for sp2 hybridization, carbon needs 3 unpaired electrons. So one electron from 2s orbital gets excited and moves into the empty 2pz orbital. Now the excited state electronic configuration of carbon becomes 1s2, 2s1, 2px1, 2py1, 2pz1. Now hybridization takes place. The 2s orbital and 2px and 2py orbitals mix together to form 3 sp2 hybrid orbitals. The 2pz orbital does not take part in hybridization. It remains unhybridized and forms the pi bond in the double bond of ethene. The shape around each carbon atom in ethene is trigonal planar, and the bond angle is 120 degrees. Now let's move towards the third example. That is benzene. In benzene, the carbon atom shows sp2 hybridization. Let us apply the trick here as well. Write the expanded structure of benzene. In benzene, each carbon atom has 1 hydrogen atom attached to it. Along with that, each carbon is connected to 2 other carbon atoms, one with a single bond and one with a double bond. So if we count the characters of carbon in benzene, there is 1 bond with hydrogen, 1 single bond with adjacent carbon, and 1 double bond with the other adjacent carbon. This gives us a total of 3 characters. So the steric number is 3, and therefore the hybridization of carbon in benzene is sp2. Now the ground state electronic configuration of carbon is the same as we discussed in ethene. It is 1s2, 2s2, 2px1, 2py1, 2pz0. And just like in ethene, 1 electron from 2s orbital gets excited and moves into the empty 2pz orbital. The excited state configuration becomes 1s2, 2s1, 2px1, 2py1, 2pz1. After excitation, the same hybridization process takes place. The 2s, 2px, and 2py orbitals mix together to form 3 sp2 hybrid orbitals. The 2pz orbital remains unhybridized and participates in the delocalized pi bonding system of benzene. The shape around each carbon atom in benzene is also trigonal planar, and the bond angle is 120 degrees. Now, at the end, let me give you a quick summary of this entire lecture. sp2 hybridization occurs when 1 s orbital and 2p orbitals mix together to form 3 sp2 hybrid orbitals. The shape of sp2 hybridized molecules is trigonal planar with a bond angle of 120 degrees. We also learned an important trick. Write the expanded structure of any molecule, count the total bonds or characters of the central atom, and that number will tell you the hybridization. If the number is 3, the hybridization will be sp2. We studied 3 examples. In BF3, boron undergoes excitation from ground state, and then sp2 hybridization occurs. In ethene and benzene, carbon also undergoes excitation from 2s to 2pz, and then sep2 hybridization takes place. In all 3 cases, the shape is trigonal planar, and bond angle is 120 degrees. Remember the rule of hybridization. The number of orbitals that go in will always equal the number of hybrid orbitals that come out. This concept is very important for your exams. Practice these examples and you will master sp2 hybridization completely.